Welcome everyone. We're to the Ontology Summit 2020 Fall Series. Today is October 23rd, 2019. And today we're going to continue the discussion from last week, trying to get a little more understanding of the knowledge graphs. In the meantime, what I tried to do was to take some of these graphs, particularly from Janet Singer and John Sawa, and I tried to put them together into a single diagram. So Janet, you provided these trapezoids, and John, you provided the loop, although I don't think I got the entire loop. So perhaps you could comment on this, Janet.
Yeah, this looks great. Yeah, I didn't put a lot of thought into the shapes that I collected, but I like the way this looks. I wanted some sense of flow without it being too rigid. And I think I also, because of the size of the text, I have the enacted outcomes in my actionable info box on the right, whereas actually that maybe should be over on the world now. So there, the Richard Verriard on Twitter had pointed to Data Ops Manifesto and the importance of having enacted outcomes or information that was actually realized in some kind of business outcomes, business value, that needed to be a fourth step on the so it's not just gaining insight, but it's actually acting on the actionable information. So I think.
Well, why don't I send this to you? It's just
well, you mean what you are showing?
Yeah, what I'm showing here is an image, but of course, I created it in Word, so I can send that to you, and you can modify it.
Okay, I'm only on my iPad, so I'm not really. I don't know if I'm the best one to edit it, but I can try. But so just to run through it, I think everybody would agree that there are important steps with the data, the collection of the data, the representation choice, and cleaning, and evaluation, and then the rules, whatever those are for operating on it, get some kind of insight produced, actionable information, important that it is communicated to both humans and machines, and then that is acted on with some kind of value realized in the world. I think that works well with what John has in the diagrams you were pointing out last week, and this looks really good as a start.
It's beautiful. It looks great too.
Yeah, actually the graphics sort of work together, right?
Yeah, I just combined two diagrams.
Right.
Essentially, I was oversimplifying I was right on the plumbing side, saying here are some triples, here are some actions, and here are some relevant triples or results. But this is a lot more encompassing and expressive.
Right.
Visually expressive too.
Yeah, there was one little, there was one icon that John had that I couldn't fit in the diagram.
What is that?
It was, what was it? Predictions.
Mm-hmm.
The predictions icon. But yeah, perhaps we could fit that in somehow.
Yes, yes, there is a lot of white space here. Can you show us what icon it was? Or it's too hard?
No, it's not hard. Let me stop sharing.
What icon is that? I mean, what did it fit?
What I'm going to do is
Talking of the diagram that is on the Ken was showing, it apparently has a lot of your ideas and Janet's and I guess Ken's, and Ken put it together as a Word document. Did you get to see it before he switched it to something that he shows about your graph?
I don't know what diagram it is, so I don't know. I haven't seen it. I've made lots of diagrams.
Are you on Zoom or you are not able to reach Zoom?
Well, I don't know what diagram it is. I didn't see it.
But John, are you able to see the telephone icon in the Zoom now? Now?
Oh, I hate this Zoom thing. I can't manipulate it.
I know, but there is a
let's see. I saw it a little bit ago. Okay, yeah, I see a telephone there now.
Yeah, now he's trying to show us something from you
Ravi Sharma
that he
letters.
wanted to incorporate in that previous diagram that he showed. So just let us be patient, I guess.
I'm trying to get to the right slide now.
Yeah.
We'll see it in a moment.
Right now we are seeing you.
There it is. Just a moment, I'm going to do a share. Can you see that?
It's coming up.
Oh, that one, yeah. Okay. Now, what's the problem with that one? It's too big, or
that has been now slightly transformed into the following. And now, can you show that again? Can you show that again?
Okay.
Yeah.
I guess the question is whether there should be four. Would there be four elements? Now, the OODA loops diagram shows the possibility of cycling within the experimentation or the thought experiments before you act on the world. And maybe we need another diagram that is more detailed. But Ken was just saying that he didn't have the prediction icon as a separate step in this, but I would think that would be
that's here.
Sort of that's a loop that one would go through before one chooses to act.
Yeah, that the deduction leads to some sort of prediction. And see, all the diagrams with the OODA loop have that from the deduction you get some conclusion.
So maybe another way of thinking of this is that the three icons on the top, one could cycle between among those three, and then one has resolved for some kind of action, then go down to the world and see I guess, different ways to treat it. Is it all four in one big loop, or is it that sometimes you need to cycle among the top three before you achieve action?
Okay, well, notice on the diagram that I have, at the top, there's a loop back for that there might be multiple iterations of belief revision. So from you select some sort of information out of your knowledge soup, and that is added to whatever your previous theory was. But when you add something new, there may be more implications, or it may require some refinement because the new information might contradict something in your previous theory, so you have to make some belief revisions in order to accommodate the new information. Then that creates a new theory from which you make the deduction that predicts something, that makes some information, gives you some information to guide whatever you're going to do as your decision. This can, in the OODA loop, there's the observe-oriented decide, and so deduction is basically the decide of the OODA loop.
Right. So yeah, that loop on the top was what I was thinking. So I didn't see that. But sometimes your prediction would just be, or often your prediction is just compared to your knowledge soup again.
Well, yes, it could just go back into the knowledge soup. On the other hand, you do want to test it against your previous information. So you don't necessarily have to make a major action. It can simply go back to your previous observations,
Right.
and so that that action doesn't necessarily have to make a separate new operation upon the world. It can simply go into your database of what you already know about the world, and then when added to the previous information, you have a new induction that goes back into your collection of little tidbits of knowledge in your soup.
Right. Ken,
so
can
if
you
I
show
may,
can you show the extended OODA loop, or extended OODA diagram, which I don't know if it's the next one.
Yeah, it's
the extended one, I guess next. There. So there's feedback possible from deciding. So that's what I was thinking about was the internal loop there, where there's observations deciding where there's a hypothesis test, and then you can loop around that until you're ready to act. So there's an internal loop and an external loop. Yeah.
Right, and that's basically that set of observations. That's sort of that set of observations. That's basically everything that you derived from the world. That and so you have a basic pot of the raw data from which you're resolving in various ways. So basically, the idea is that that loop with the purse in the middle shows the four basic operations of induction, or the three basic methods of reasoning, which are induction, abduction, and deduction. And then the fourth one is testing. The testing is where you go back to the world, but that could just be going back to your previous set of observations. So when you have that diagram of the world, it can be all of your previous knowledge that you obtained in previous observations, as well as any new ones that you add to it.
Right. So it could be your model of the world, or it could be effective action on the world.
Yeah, it's basically your mental model, that there's the world outside and there's your mental model of the world. And that mental model is not an exact picture of the world, but it's the best that you know at the moment.
I see. Yeah. So we probably do want to have a diagram that explains all of this with the model of the world. Would you say in your diagram there that the model of the world, that the world icon represents the model of the world primarily?
Well, it's basically what you have. It's the world as you observe it. so that I just put that diagram of the world, but you could just say that this is, there's that, in my slides there, I have another one of the slides where I show the difference between the world and the model of the world. That you have your, there's one of the diagrams where it talks about a Tarski style model, and your theory is based on your
implementing the cycle or something else.
Well, oh, let's see, I don't have the slides in front of me.
42, slide 42. Is that the intentional context? It's
one way. There's a slide that talks about I don't have the slides in front of me. So
you tell me what it is, I can look at it. I'm at your slides right now.
I would have to.
Okay, I can say something. Extended or OODA loop, then there is a H-COGAF architecture, then Albus cognitive architecture, and implementing the cycle with the same OODA. Open-ended variety of methods for learning and reasoning.
Okay, let me.
Probably can show those, and then you can decide which number it is. While we are at it, I'm having a question. Is prediction same as what I used to call results in some of my slides, or whatever is the result of a search, for example, Google search or whatever search, when you get something,
Ken, if you go to 44, slide 44 of John's.
Oh, I tried putting in some feedback loops here.
39 is also.
And 39.
And 44. 39 is not numbered. Oh, you mean, John, you mean models of the world?
Yeah, I'm trying to get I'm not using my regular computer, so I have to go to this disk, and I have to go doing a bit of searching to see what I had.
Yeah, I think this and this one is helpful, and 44 is the one he was talking about with the world and the world model.
Yeah, I think it was 44, I think, Janet.
But this is also, I think this 39 is something we should focus on. Do you see that, John?
Okay, yeah, that looks good. Yeah, that's the one I meant. It's the model of the world. And so the model of the world is basically in some sort of symbolic form where you have, and I show it as a graph, where the nodes represent the things that, the things and the various things in the world and the relations among them. And so your theory is a set of statements in some version of logic or language, and the model in the middle, or the model of the world, represents whatever we know about it in whatever view we have of the world. And that model is always an approximation to the world. And the theory itself has a precise mapping to and from the model. And in terms of the model, every statement in your theory has a denotation of very precise true or false. But the fuzziness occurs in that mapping between the model and the world, because none of our mental models or our computerized models are exact representations of the world. There's always some kind of engineering discrepancy. There's the engineering tolerance, and there's the errors in measurement in your science. There is the discrepancies between your scientific theories and the actual theories of nature that govern how the world works. So there's always this approximation there. And so when we're talking about that world, we have to make a distinction between what's really there and what's in our model. So we're always we're always refining our model. With every time we go around that loop, we make additional observations and we test our predictions against the world to see how accurate they are. And from that, we get new data, which goes into our, which refines our model of the world.
Okay, where are the knowledge graphs?
Well, the knowledge graphs
are... process seems to be the knowledge graph.
The knowledge graphs
right?
represent some model of the world. So they represent all the facts in our knowledge soup. And actually, there's a huge amount of stuff in that knowledge soup that is not really consistent. So that the knowledge comes from all kinds of places. So like if you take that Wikidata stuff, that comes from all of the Wikipedia articles.
In this slide, the world depicts the knowledge pool.
In this slide here that shows the models of the world, real or possible, that model happens to be a one consistent view of one subset of the world. But the knowledge soup is a conglomeration of all the possible views of anything. So for example, think of Wikidata. Wikidata is derived from Wikipedia. Wikipedia has millions of articles written by many different people from many different points of view, and each article has contributions from many people with different points of view. So you can't consider anything in Wikipedia to be consistent either within a single article or across all the articles. So that Wikidata is just a huge knowledge graph of all kinds of stuff from all kinds of sources, and with all you know is that these are all kinds of assertions that come from almost anywhere, and you have no idea how accurate they are. You just pick and choose among them.
Yeah, I don't think we can fit, I think we need multiple graphs. I think we need another layer here to show the data and the knowledge graphs. You know, in addition to this world model theory relationship is more, this is at the ontology level where you actually have, you know, you've been working on the consistency of the relationships, and this is maybe the best that you can do, whereas the data-driven side would be more like a layer below this of where you get the models and theories from.
Well, again, when you talk about below, up, above, and below, those are relative to some diagram, and so
right,
unless you have a specific diagram, you can't really talk about above and below.
I like the first diagram that Ken had, a very simple one. I don't know if we have the right text or the right graphics and the right arcs, but I think that we should aim for something that is that simple. And then we should have some elaborations that go into these, into 39, where you show the relationship between the basic loop and what a computer adds to it. At 39, 44, you know, the extended OODA, and I think that's a, anyway, I just think they're similar but different perspectives. Yeah, good. And it would help in the communicate to have, you know, four or five diagrams that would show how, you know, how all of these viewpoints fit together, and then the knowledge graphs would be, you know, the question Robbie raised there. Where are the knowledge graphs, or was that Ken?
I raised it.
Yeah.
So the knowledge graphs are in the knowledge soup.
Right.
right?
Yeah.
Oh, wow. Now, what is the difference between prediction and results?
Well,
John or Ken?
How are you using results? Is that
No,
the
when
actionable
it says
information?
prediction, is that not the same as result? Suppose I do a Google search. What do I get? Predictions or results? I'm just using a simple example of I do a search and I get some results.
A search is just going to
be the
part,
same as prediction, or is prediction another concept?
Search is just a part of your decision loop. Question is,
See,
what's
we
your
are not
purpose
deciding something inside the theory or within the actions of this. Maybe it's the what you call trapezoidal cube or this hexagon type. I mean, whatever you call that. Buckminster Fuller structure or a polished diamond, whatever you want to call it, that is where a lot is happening. But the result of
right in John's picture,
result of that is prediction. But prediction is coming before actionable. So prediction should come before the actionable.
Well, you're predicting
because you will still
world.
filter the prediction further before you act on it. Or is the act of filtering called actionable info?
I'm not saying that this is anywhere near a final.
No, but it has got all the elements, so we are just talking about it.
So
at least you have created a near, something aiming towards the knowledge graph concept we want to convey. But I'm requesting some little ordering in my own mind as to how we go about it. Suppose we do a simple search using Google. It's in the background, they call it knowledge graph. So we get a lot of results. Then there are other filters you can use, or you can go instead to an advanced search, Google advanced search, or you can go to Google Scholar and refine those kinds of results to get better and better what you are showing here as prediction. But I think that is result, not prediction.
You may have leaning downstairs. I'm not sure.
John, your comment or anybody's? Janet?
No one knows our area. Oops.
Okay, I did go through my slides.
In the basement, just go down the stairs and turn right until you get around to the back of the stairs.
Okay. Yeah, I was just looking at those slides. Again, I managed to get back to my old slides. So that on slide 35 of that misc.pdf, there's a very simple diagram of Boyd's original OODA loop, and that's something that a lot of people have come across in one way or another. So, and it's a very, very simple one that just shows observe, orient, decide, and act. And that by itself is a good one to keep in mind because it's so simple that people can remember that. And the idea is that you can.
Is that slide number?
35, and this is my misc.pdf. That's
I was thinking the same, John. No, I was thinking of 36. 35 is Boyd's loop.
Yeah, now 36. Yeah, now 36 is the extended one. This is also written by John Boyd, but the thing is that 35 is so simple that everybody can remember that. And so it's useful just to mention that. Here is, it's just a little one that you can put that in the corner of the document so that you introduce it by saying this is where he started with. And then you go to 36, which shows the extended OODA loop. And Boyd's original one was designed for very rapid response. He was training fighter pilots. He himself had been I think he was in the I think that it might have been in the Korean War, where he was involved with his own activities, and then he later got into he was in more general DoD sort of area where he was training fighter pilots, and he needed to train them to respond within milliseconds, because you've got to be able to respond as fast as possible in order to survive. Now, then later on, he had been working with a broader range of people who wanted to apply that same idea to longer range planning, and that's where he developed his extended OODA loop. Now, this version I took straight out of the Wikipedia. Actually, the Wikipedia had a little more detail, and I deleted a little bit more, some of the detail to make it cleaner and simpler. And so that's the 1 in 36. So one way to handle that is to just show different viewpoints of the same sort of thing. You first start with the simplest OODA loop, which just tells you the simplest part, and then you can go to 36, and then you can go to, now then it shows that other people, 37 and 38, show versions by other people who independently developed their versions, and they all have those same basic 4 steps, and they may have this intermediate one, that the one on 38, this is from Albus, that who had developed, who had been combining his work in neuroscience. Well, actually, he started with computer science, but he then adapted all these ideas from computer science.
I want to ask a question, John.
Okay.
When you are showing that extended OODA, that's comprehensive. It conveys a lot of concepts. And now look at 44, which is Tarski style. What's the difference between Pierce or Boyd style and Tarski style?
Okay, this is.
It seems to say the same thing, but in a different graphic way.
Okay, the one by the system by Peirce and Boyd and others all relate to the process. They talk about the process of how do you develop a theory. This one on slide 44 by Tarski is after you have developed your theory. This is a static view of how the model, in the middle is the model of the world expressed in some sort of graphic form. Think of knowledge. If you want to think of that, you can either think of that as a formal logic, where you use precise terminology, or you can think of it as a knowledge graph. And whatever it is, that model represents your current view of the world. And this model is something expressed in logic, and your theory is always a statement about the model. So your theory can be whatever computerized application you're working with, and the statements in your theory have a denotation, true or false, in terms of that model. And that model is an approximation. It's always an approximation of the world, and that approximation can be good, fair, or poor. And that's where you get that idea of the fuzziness. Fuzzy logic shouldn't really be considered a statement of truth or falsity, but rather an estimation of the level of approximation. How accurate is your model of the world? And
okay, I agree so far. But I see in this diagram that the two arrows are the bottom two arrows are independent of each other, while I think they should be linked somehow.
Wait, which bottom? On slide 44 or what?
Should, sir, the denotation, true, false determination should be related to the approximation.
No, you have to keep them. You have to keep them absolutely separate, because the denotation talks about how the theory is related to the world. Your theory is your computer applications. Think of it when theory there. I showed theory in logical form and logical statements and or a predicate calculus.
Yes.
But you can think of that as your computer. Your computer always assumes things are absolutely crisp and clean and precise. So that can be your computer application, which is using data from your model, and the statements the statements in your computer are true or false about the model. Now, the model, however,
nothing to do with data.
The model is your data. The model is your data. The theory is your computer program. Your computer programs can be stated in logic, and you use a logic programming language like Prolog or SQL, for example. That's a logic-based language that you use to access your model.
No problem there. No problem. I understand. But what I don't understand is once you have denotated that, then the result of this should feed into the approximation.
Now you're talking about the loop. The looping thing, that's the process. This is, slide 44 is static. It's a static representation that shows how the theory, which is implemented in some computer program. So on the left-hand side, instead of theory, you could put there software, programming, whatever. And there you have this theory is always true or false, making true or false assumptions about what's in the thing. So, for example, if you're using SQL as your language, therefore you're accessing your database, SQL makes the assumption of negation as failure, so that if it fails to find something in the model, then it assumes that statement is false. And so there you have SQL, and so SQL is accessing a database. The model happens to be your database. The database can be represented in graph form or in table form, and I keep emphasizing that graphs and tables are logically identical. There's no logical difference between a table and a graph. They're just different ways of representing the same data. And your theory, instead of theory there, you can think of your programming language, which can be logic-based, like SQL is logic-based, or it could be a software, programming based, but whatever it is, it's implemented in very precise notations, which assume that the model is the data about which things are true or false. Then the approximation is always based on your measurements. It's based on going out with your instruments, with your measuring instruments, your telescopes and your microscopes and all those things that check to see whether your model is accurate, is an accurate model of the world, and it's never absolutely accurate. The only thing is whether it's accurate within the level of engineering tolerance or the approximations that are adequate for whatever application you're doing.
Okay. I think Paul Tyson has a nice thing on the chat.
Yeah, let's see if we can get
OODA 2 steps.
See if we can get some more. See if we can get some more people involved in this discussion. Okay.
All you want to say something?
Todd, David.
You really want me to open my mouth, Ken?
Go ahead, Todd.
Well, Ravi, I was just typing in the chat that the distinction you're looking for, and I think John made clear, is that the Tarski model is a static interpretation of a theory, whereas the OODA loop was designed for dynamic knowledge evolution or change of knowledge. And in particular, I think it assumed, at least initially, that you had some implicit base of knowledge for which you were going to compare your current state against. And then if the current state required a change in that implicit knowledge base, well, you make that change or you get yourself killed. So, I mean, the dynamism of knowledge bases is not addressed in current work, to my knowledge, to any great extent. I mean, there is the notion.
So you mean the 44 does not show the dynamism, but the slide 39 does?
Well, that's what John was saying about slide 44. It's a static environment. It represents a static view of your theory as interpreted in your model. Now, if your theory
Otherwise,
changes,
the two are similar or congruent in concept.
I don't
That was
remember.
my question.
I don't remember what is on slide 39. Who's driving the slides?
I am.
39 is extended OODA. Extended OODA.
I got the 39.
Yeah. So, I mean, it necessarily looks like if you go to the the fourth quadrant, it's where you have an abduction going on. You're considering changing. In fact, it says belief revision. So it doesn't necessarily talk about theory per se, but belief. And maybe there's some theory that you can formalize behind the belief, but there's an assumption that you have some implicit knowledge or implicit beliefs that you were acting on, but now you've got this new information and you need to modify that. And in the case, the original development of the OODA loop was to stay alive. So whether you can have active, what they call, I believe, active learning in parts of what is a euphemism called AI, you can modify your knowledge base. I don't know how dynamic that is, and I don't know of any instances that are actually done in practice.
But the thing is, can you also say that you are filtering the knowledge base by going to more and more relevant things dynamically? So that is like a action, you know?
Well, that would depend on the extent of detail that's represented in your initial database. If you have a huge amount of detail just within as in a relational database, you make some cursory query to sort of scope out what it is you might make further investigation or queries against.
Just a simple example is entire elements of periodic table and then pre-selecting only metals out of it.
Yeah.
But well, the other thing is that the chemists have done a tremendous amount of work in analyzing and massaging their data. And if you go to your handbook of chemistry and physics, they always represent their data with stating the value plus a tolerance. They always state for any measurement, they give you the best value, the best known value for the speed of light, and then they tell you what is the estimated error in their measurement, or the engineering tolerance. So there's always those two numbers. There's the best guess, the best value, plus a measure. Now, one of the problems with the knowledge graphs is that they tend to mush it all together. Like, for example, if you look at Wikidata, Wikidata is a huge knowledge graph of all this stuff that was extracted from Wikipedia. But every Wikipedia article is an independent article written by several different people. And so even within a single article, you can't be certain that every piece of information there is consistent. And then when you when you munch together all of the Wikipedia articles and you extract this huge knowledge graph they call Wikidata, you have no idea where these little pieces come from.
Well,
and
no, John, John, be careful. That's not exactly true. The page, hold on, Ruffy. The pages on Wikipedia are not independent. I mean, they are linked to other pages. So there is some notion of some consistency. Whether it's completely consistent, as you're pointing out, is another question.
Well, yeah, but the point is that one of the reasons why I use that metaphor of knowledge soup is to emphasize that there are all these little fragments that have been derived from all kinds of stuff. So that the knowledge soup is supposed to be everything that's in our head that we learned from infancy on up, and some of it that has been sort of, we have through our own personal views, we have sort of polished it up and formed some kind of more or less consistent views. But when we go from one topic to another, we're switching to a different area where we have a different viewpoint in which we may be looking at the same things from a different angle and point of view, and it may be totally inconsistent with everything else we know.
Well, one item that seems to be overlooked in all of this discussion, and I'm guilty of it also, is that we don't have any good notion of what knowledge is, or any precise notion of what knowledge is.
Right.
So we just bandy that term about, and we all think we have some idea of how to interpret it, and obviously we do, since we're able to communicate to some extent and make actions based on that understanding. But we don't have a very, I hate the word, well, I won't use it.
There is not a single idea, Todd, I think.
Yeah, probably.
There is
this notion
a
of knowledge
variety of sources of knowledge, variety of databases, variety of what is in our head, as you say, etc.
Well, a database by itself may not be considered knowledge unless you have some way to interpret the labels that have been used to make distinctions.
No, we were talking of knowledge soup.
Well, I think that's
consist of several inputs from databases, from what we learn, from languages, from our mental models. Everything is in the knowledge soup.
Hey, John, have you copyrighted
So
that phrase yet?
there is not a single definition of knowledge soup.
No. What was the question?
Have you copyrighted this notion of knowledge soup? I think it's quite appropriate.
Well, that's a term that I first started using in 1987. Now, I have not trademarked it.
I'm teasing, I know.
Yeah, it's not. It's the kind of thing that could be trademarked, but I didn't.
First, you have to get the URL.
Well, I think it's an appropriate term we should not forget, because it does suggest that there is confusion about this notion of knowledge.
Yeah, I have several papers on it, and you can cite the paper. There's an early paper, one of the papers in which I define it fairly clearly.
A question, Mark?
Mark is writing very good things, yeah.
Mark, are you on the...
Mark, can you
Hey, Mark,
speak?
could you, on your comment on at 12:50 Eastern Time, you have this unfair complaint. Could you expound on that?
Well, I think the discussion, is my audio working? I'm not sure about Zoom these
Yes, it
days.
is. We're receiving. I'm receiving.
Okay, thanks. So I think John's level of abstraction is, you know, for lack of a better word, a higher level tackle on this. And I've missed out in the last couple of meetings, so I'm not able to make the proper connections here. But, you know, the starting point for a lot of problems that I'm facing with using some of the ontologies for cybersecurity is using things that are traditionally graphically represented, like network graphs and attack graphs, and connecting them to things that do have existing ontologies, like the distributed task force representation for IT, which, you know, defines what a server is, and that servers have power supplies and network addresses, and that there's this seems to be something that would call out micro theories, as opposed to something as abstract and wrestling with topics like, well, what do we actually mean by knowledge? I think from the practitioner's point of view, we don't ask that question. We're more wrestling with a lot of assumptions that we take for granted, and we're trying to pull levers on existing connections, like the ones that are surfaced by attack graphs and by network graphs.
Well, yeah, I mean, that's correct. I mean, and there's nothing wrong with that. I think the only issue that you might run into long-term is interoperability, because unless your ontologies that are underlying your information systems have some ontological coherence and consistency, you're going to run into problems as you try and extend it. But from a very practical point of view, what the heck, go ahead.
Now, I would agree with Mark that basically we do not need a definition of knowledge. That's not going to help.
No, yeah.
What we can simply do is, in these diagrams, I don't talk about knowledge. What I do is talk about a theory is a formal statement in some sort of formal notation of some kind, and that can be your RDF or OWL or predicate calculus or common logic. But then you can also have informal theories, which are just stated in ordinary language. But in any case, what you have to do is distinguish different theories. So there's an open-ended variety of theories stated that may be consistent within themselves. They could be informal ones stated in ordinary language. They can be more formal ones stated in some kind of computerized or computerizable notation. And so those are the things that, but the thing is that there's a huge number of theories that are derived from we now have over half a century of computerized systems that have developed various kinds of not ontologies that are implicit in their implementation, but that have never been broken out into some sort of even an ordinary language kind of description. And but the thing is that we have our descriptions of what we know or in what is known in various domains. And those descriptions are the only things that we have to deal with. Those are things stated in logic, English, diagrams, or whatever. And then we have the, by the knowledge soup, I meant the totality of all these little chunks of that are bubbling in our soup. These are little pieces of knowledge, which may be small little observations, just a little an email note, for example. It can be a little diagram. It can be a larger report or document or whatever. And all of those things are all related somehow. And then we have to, from that, we have to, for any particular application, we have to extract from that what we need for our application and relate it to other applications that have been developed by different people with different terminology and in trying to communicate among them.
And John, as you pointed out more than once, that last item that you just mentioned, trying to have applications communicate with each other, that is the interoperability problem, which has been persistent for some time. Now, one other point that I want to bring out, and I think it gets glossed over to some extent, is that natural language is the basis of, well, obviously for communications among humans. However, the notion that having a formal language, whether it's first order logic, second order logic, modal logic, or whatever, all of the uses of those formalisms are done by humans. So independent of whatever symbols you're using, whether they're natural language strings or just, you know, whatever characters or graphics you want to use, it's people who are going to have to interpret those. And you hope that you have provided them with enough guidance so that their interpretation is not going to be too dissimilar from what you intended. But again, all based on natural language. So, I mean, I can have a wonderful first order theory that describes whatever foundational ontology or whatever network ontology you want. But if I just use a bunch of symbols, then as your one diagram on 44 point shows, I can have all sorts of interpretations, and i.e. models, that may not be consistent or even anywhere near what I had intended when I first developed or tried to express the formal representation of my theory.
Yes, and I want to emphasize that the people, the professional programmers and data analysts and so on, those are people who have been trained to think very clearly and precisely about how they map this informal stuff that they learn about the world into some computerized kind of form. But the people who are going to use their software, these are the clerks in the ShopRite or some or the nurse in some hospital. These are the people who are going to be entering data into your system, and they have no understanding whatsoever of all the assumptions and logic and programming that you put into your computer system. All they have is some manual, which they probably never read, and some basically some tutorial by some guy who stood up in a meeting and gave some slides and talk, and which they sort of sat through and listened to, but forgot when they're actually entering the data. So you have to remember that. You have to think about the nurses and the clerks in the stores, and
John, I'm sorry, don't forget about the labels that those people would see on their user interface. Right, those labels are in natural language. And they're
yes, of course. That's what I mean. Absolutely. Okay. And the people to have no idea what those labels are. All they see are these words.
Well, I'm sure if they're a nurse or a doctor that's entering something into their I forget what you call those systems, they probably have their understanding of what those terms are. However, how those terms have been interpreted in terms of the information system is another story.
Right. And you also have to remember that when you're talking about healthcare systems, we have the patients, the nurses, the
Doctors?
pharmacist,
Yes.
the physician, the general practitioner, and then the specialist in every possible area, and the orthodontist, and the surgeon, and they all have their own versions of these same things. So we have each one of those people has a slightly different vocabulary, and and when they share the same vocabulary, they have a different interpretation of it. And when we're talking about word senses, remember all that discussion about word senses, they all have a different selection of word senses that they're attaching to those labels.
Mm-hmm. So the one hope of using an ontology is that you can perhaps constrain those interpretations, but you can still
you're constraining the interpretations for the computer, but the people are still thinking in their same old way.
Exactly.
But you're also constraining the interpretations if you force the people using the electronic medical records to the constrained interpretations that the developers thought were appropriate when they put the system together. Then you get a lot of pain as well, which electronic medical records are, have quite a bad record and a lot of...
and that's an issue of the development itself. And whether
that's the example of a soup, Janet.
And
electronic medical records are like a knowledge soup.
When we talk about knowledge graphs,
we have to make some sense out of it using either knowledge graph, search engines, or whatever we are talking about in this summit.
Again, a knowledge graph taken from some scribbling by a physician, an internal, basically your general practitioner, the surgeon who did the operation, the nurse who was in attendance, the pharmacist who was making and providing the drugs. They're all using different interpretations, and then the patient who was describing his or her symptoms and pains and suffering is also there on the record somewhere, and all of them have different word senses and based on different informal ontologies in their own personal knowledge soup.
And they have different representations, like data graphics for X-rays or MRIs and so on.
And the X-ray technician is going to be different from it has a different interpretation from the physician who is looking at and treating the patient and all of that.
Right, and this gets out, John, what you were talking about last
week. In our
discussion,
I see that these couple of graphs that you all have put together, we all have put together, including John and Ken and Janet, are the best we find so far that are relevant to the topic of the summit, unless there are others.
I don't think we need to search. I don't think we need to search for others. It's more a matter of refining and integrating what we have in these half dozen graphs. And I think the fact that these different issues about the the ambiguity in the world, as John was saying last week, is handled in natural language somewhat robustly, and humans communicating with each other using various ways of signaling meanings and negotiating meanings.
Oh, yes, negotiate. Follow-up questions are absolutely essential, and that is the way people can clarify that they don't really understand one another's language directly, but they can ask a question, and that ability to ask a question, and this is another problem with these question answering systems. They're designed for just one question and one answer, and what you really need are follow-up questions so that you can drill down to get as clear and precise an agreement between the two people, the people who are talking. You can't just when a patient goes to see a physician and asks a question, that patient is not going to understand that answer immediately, and there's always going to be a dialogue that can be a fairly extended dialogue before the patient is satisfied that he or she has enough information to be able to take the drugs correctly or do the exercises or do whatever is necessary to aid in the recovery.
So the ability to handle the ambiguity, negotiation, and in natural language in the world, on the one hand, is complemented by the precision and rigidity. Precision, maybe on the positive side, rigidity on the negative side, in the formalized system, and the unnatural language, as Eddie keeps saying, that both of these pictures are irreducible. They both need to be handled in our contextual diagram here. That knowledge graphs are to be understood as negotiating between the world of ambiguity, natural language, human communication, human-to-human communication, and computerized, precise, rigid, brittle, but consistent, formal value theories. So, Robbie, you were asking why can't this be simplified? But I think it's important that we not simplify things, that we have that we show the articulation between these different aspects. It's more a matter of how well you handle all these different elements than trying to get to a simple, one simple view.
Okay, great. But we're running a little over, and people have to leave. So I think we're going to have to.
I request others to comment if they've not already put it in the chat.
Put things in the chat, and there have been some things in the chat, but we're going to have to close this meeting today and continue at a later time, hopefully after we have done some more work on these diagrams. So I wish to thank everyone for joining us today. And I'm now going to